Thanks, Misha, and thanks for the organizers for the invitation. Quite sad I couldn't be here for longer. So yeah, this is actually motivated by some discussion very long time ago when we were talking about regularized estimators. Like I think that was in Europe's paper 2017, and Misha walked by, and then he was like, "Nobody is regularizing anymore," and so. Yeah, so this is a little bit on that line, and maybe I'll start with some motivation by explaining what Misha was saying back then, and then what we figured out theoretically to understand what's happening. So this is work based on some papers that I wrote together with my PhD student Konstantin primarily, and for this particular work, Stefan and Nicolo also did a bunch of experiments and also proofs. Okay, so what's the phenomenon that we find surprising? So a lot of you have heard of this double descent. I just wanted to be a bit more precise about what exactly is surprising about that curve. There are many different phenomena, and we're going to focus on a few in particular. So, okay, so just to those who are not familiar with that yet, so what is the double descent phenomenon? So we will look at a particular experiment. This is an old paper by machine learning standards, an old paper, 2020. And so they did an experiment with C410, which is like the classical old image classification benchmark, where they added 15% label noise just to make sure that there is noise, right? So if you don't have noise, there's no problem of overfitting potentially. Okay, there's still the problem of finding the right function, but overfitting is not the problem. So they add artificial label noise, and they're running some standard gradient descent or first order method on neural networks or ResNets. This is kind of old, but still the phenomena are interesting to study. Okay, and so what they find is, first of all, as we increase the width parameter, right? So we have neural nets of different widths, so more and more parameters. The beginning, the training error goes down. So as you grow your model size, you can train the error on the training set to smaller and smaller, or you get a better precision on your training set. But then on your test set, the error goes up, right? So this is the typical U-curve of the bias variance trade-off, overfitting, etc. Right? And then at this point, we have a pretty good, basically the training error is very close to zero, or at least it's much smaller than the noise percentage. So we would say we are starting to fit noise. And so this is when we kind of pass or go past the classical regime. And we enter the modern overparameterized regime where you could fit the data perfectly, and even beyond that. Right? Well, why should you ever do that? So that's why nobody has looked at this regime before in traditional settings. And what we find here, like in practice nowadays, people like to use overparameterized models also because of optimization. Things just train better, etc. So this is why this started to become relevant only in the recent years, this regime. And we also see that actually the test error goes down again. And so it's not actually blowing up, as you might expect the U-curve to go, but actually goes down. That's also why overparameterization has received a lot of attention. Okay, so this is the double descent curve. We have a first descent because, well, that's when we can actually start fitting anything. So we have enough expressivity, but after that, we have a second descent, which now we know where it comes from, but it was originally puzzling back in the days. So the second descent is kind of well understood now, and I won't go into detail if you're interested. We have a NeurIPS tutorial together with Vidya also, it's in the audience, and also gave a talk earlier. Okay, so the first thing was the double descent. The second thing that you can see is the following, which here you need to parse a couple more curves. Right, so the blue curve is what we saw before. If we train the network until convergence or until it basically, it doesn't decrease anymore in training error. And so what you could also do is not train until convergence and stop it at some earlier epoch, right? So here's the different curves correspond to neural network stopped at certain epochs. So the yellow curve is all neural networks trained only for a few epochs, and then the darker it gets, the longer it's been trained. Or the different ones have been trained, right? So every x-axis point corresponds to a different size neural network. Okay, as you see here, so what you want to focus on here is to compare the one at convergence, which is the blue one, with, for each width, the best stopping point. Right? So for example, if you're here at, I don't know, 10, right? So you look at the different stopping points and you see, okay, the best stopping point is on some green curve, it's like somewhere here. Right? And then I move further down, and what you see is that the best stopped neural network and the neural network at convergence, they have the same test error at some point, which means that stopping early is not helping anymore. And stopping early corresponds to essentially not necessarily training, or not as essentially getting 100% accuracy on your training data, or at least not waiting until the loss goes down much further. Okay, so what you see here is that for somewhat models that are kind of close to the interpolation threshold, where you just start to fit in the noise, or you try to basically perfectly fit, at that point it's super critical to regularize. So when we say early stopping is essentially a regularization, that was the paper 2017 that Misha was walked by and said you don't need it anymore. Around here you do need regularization, but then as you increase the width, regularization just doesn't help anymore at some point, and interpolation becomes harmless. And that is the second observation here. One is the double descent. You have two descents. The second is that for large models, interpolation becomes harmless, or regularization becomes useless. Okay, that's the second somewhat surprising part. And the third point is also that for these large models, they get reasonably good accuracy. Still not perfect, right? So they still have 30% test error. You can say it's high, but you might expect that if you really fit noise perfectly, that you should perhaps get large error. So it still does reasonably good. Okay. So these are the three observations I wanted to point out in this. There's more that we will not discuss. So what do we do with these observations that are purely empirical? Right? So now deep learning has uncovered some interesting phenomena that we're not so sure intuitively why they're happening, based on introduction to machine learning and also statistical learning theory. So far, we were not able to really understand why these curves look like this. And so this kind of inspired a new line of work that is trying to understand this, what's called Benabur fitting or harmless interpolation. And yeah, we've proved a couple of theorems, not just we, I mean the community proved some theorems. Some of them are kind of specific to very certain, for example, covariate distributions, etc. And so primarily focusing on linear models. There's also some nonlinear work, but so this is kind of what we've been doing. And so this is also what I will tell you a bit about today. It's more about the theorem statements and less about the techniques because they're quite specific. But the theorem statements at least let you get a hint of why this could be happening, or at least in some toy settings why this could be happening. And it's kind of, I would say, statistical theory that's useful for these particular settings. It's unclear how they will transfer to explain the original experiments. Just to be clear, for me, it is an interesting kind of question to think about because it's counterintuitive even in a simple setting. So it's mathematically interesting. And also, towards the end, in the second half, perhaps I haven't talked about a lot, also has unveiled interesting phenomena that we do not have theorems yet for, and for which we might need some more proof techniques also to understand, to understand those. Okay, so let's talk about the actual content. So just before I go to the theorems, the goal is not to find better interpolators to use in practice. Like, because I said, okay, regression is not helpful anymore, interpolation is harmless, so how should we interpolate? That's not really what this talk is about. So I just want to focus on understanding when it would be fine to interpolate. And so when you end up interpolating, it might be, and it works well, and it performs well, generates well, what are possible reasons why it does, and when could it not, and when could it perform well. Okay, so the setting will be sparse linear classification. I will go through that in the next slide. And importantly, it's because even for linear models, you see similar curves as well, and that's why we think it's worthwhile studying those. And particularly, we'll talk about max LP margin linear classifiers, and we'll focus on two questions. And the first question is, if we have noisy observations, and we use max margin classifiers, what are tight rates for P in between 1 and 2? And the second question is for noiseless case. Okay, so for the noiseless case, are max L1 margin linear classifiers actually adaptive to sparsity? And this is answered easily for regression, but for classifiers, actually nobody has looked at that in detail. So this second question is perhaps the one I've talked about the least. Okay, and both of them will have some surprises. Okay, so sparse linear classification is to get the setting right. We start with some W star, that's our ground truth vector that's going to govern whether we classify as 0 or 1. So we can think of it from a signal processing perspective. You want to recover this W star, which is sparse. So the sparsity here, a 0 norm is equal to S, smaller than N, much smaller than N. And we have a lot more dimensions than we have measurements. We have N measurements, and the dimensionality of W star is D. And we assume that it's Newton norm for simplicity. Now, how do we want to recover W stars? From measurements where we just take X, which is a data matrix, and multiply with W star. These are our measurements, and not quite. And then we take the sign of X W star. These are with some noise, and these are our measurements, so maybe that's here. Right, so we first do X, which is a Gaussian matrix of dimensionality N times D. Right, N much smaller than D, so it's like a wide matrix, and you multiply by W star, and then you take the sign of it and have some label noise on top, and that's what you actually get. You get Y and X. You want to recover W star from that. So the label noise that we assume is a large class of possible noises. The only thing is that it should, if it depends on X, it only depends on X in terms of the direction of W star, so in terms of the scalar product with W star. So this could be random label flips. It doesn't depend at all on X, or it can be, for example, a logistic regression model. Okay, so how do we measure performance of some estimate W hat? We want to compare essentially how close it is to W star, but only, we don't really care about the norm. For classification, we primarily just care about whether the angle is close, and that's why we look at this this measure here. Like W star is unit norm vector, so this is essentially the angle, and this is also close to the prediction error when we have a relatively small prediction error just by Taylor expansion. Okay, this is what it's gonna be setting for the talk. And okay, so before we go into classification, I just wanted to give our sparse classification. Let's recap sparse regression, because that should be a bit more familiar to most of you probably. So in that case, our measurements, we also want to recover W star, but our measurements are of this form. So X W star plus some additive noise. That is in the regression case, and we don't have the sign in front. Right, so we have continuous measurements, and we want a small error W hat minus W star. Okay, so if we know that W star is sparse, what we're going to do is something like the lasso. If there's noise, and if there's no noise, we're going to do something like basis pursuit, where the key is that we want this W hat to have small L1 norm. to induce sparsity. Right? So in both cases, so in the noiseless case, what we want is that we have interpolation, right? Because we don't have noise. So you can just say we want the true W star satisfies this, so why not just enforce this constraint? It helps us, right? And we want, among those that interpolate, we want one with a small L1 norm. So we're essentially constraining our space in a useful way. We're having an inductive bias that is towards the ground truth W star. So we have, these are all known things. So we have a perfect recovery with just n of the order of s samples. In the noisy case, we have a minimax optimal rate with the lasso for an optimal lambda of square root s over n. Essentially, 1 over square root n is the rate. Okay, so this is all known. This is our intuition is that inducing sparsity helps to a large degree in the rate, right? So if you didn't have sparsity, you would have a d over n rate, or a square root d over n rate, and this goes down to s over n if you have sparsity. So this is important when d is much larger than n, of course. You actually have a chance to recover W star. Okay, so now let's go. Okay, so one important thing here is what we did here in the regression case. Right, in the noiseless case, okay, this doesn't work. In the noiseless case, we enforce perfect data fit. And that makes sense because we don't have noise. Why not do that, right? In the noisy case, though, we have to sacrifice data fit in the lasso. Right, so we're trading off the L1 norm and a data fit, and which means we really have to make sure that y is not equal to xw because the ground truth doesn't satisfy that, right? So we want to enable there to be some slack in the data fit, so that we can focus on what we know, which is that the ground truth has a small L1 norm. So this is important. In the noisy case, so far, this is classical regime, what people have studied: noiseless, perfect data, noisy, sacrificing data fit. So, okay, so first of all, what's sparse classification? Similar, but now we have the different measurements. We also want to recover W star. So what have people done there? Right, that's a bit less known, perhaps. In the noiseless case, you can study this non-convex problem and try to minimize that non-convex problem using first order methods, and you can also show a convergence to a good point that achieves this rate. Okay, so here we also have perfect data fit. It's not y equal to xw anymore. It just says that for every point, so here in this case, xi is 1, sorry, so you don't have any noise, right? And in that case, you just want for all xi's, the wxi to match the yi, just that the signs match, right? Then you have perfect data fit in the classification sense. And so this the norm equal to 1 is just to make the solution unique. And so you can get this minimax rate s over n. You can get it with this algorithm, binary iterative hard thresholding. Okay, so this is not, but this is a non-convex problem. Okay, so when observations are noisy, there's also some results for the rate, statistical rate. However, okay, the rate is of order square root s over n, the best one. However, here you also sacrifice data fit. So what's happening is you're not minimizing, you're not maximizing the min margin. So min means the min over all, like you don't force this to be large for all yi, xi, but you want the average margin to be large, right? So the average of these values yi, w, xi to be large. That means you could, basically, it could help that if one of them is particularly large and one of them is small, that you have some compensation going on, which is not possible for this kind of min margin mindset. So if you use this instead of the average margin, this would be a completely different problem. Okay, so here we explicitly have this sacrificing data fit also burnt in to the noisy frameworks for which we have rates. This is essentially the analog to regression. Okay, so here there are two things. So first of all, this is a very particular. First of all, this algorithm is a very particular one that's running gradient descent on this. And what you get out of is a bit non-interpretable, or it's not a standard classifier you would find. So it's it's kind of, that's one thing. And the other one is we want to know if we are enforcing perfect data fit, what happens to the noisy case, if we are enforcing perfect data fit in the noisy case. Yeah.
The noise is multiplicative?
What's that?
The noise is multiplicative? The noise,
yeah.
Is it additive or multiplicative?
Sorry, multiplicative, yeah, like here. It's a times, basically, so for every xi, you have y equal to sine of xi transpose w star times -1 or +1. And that is, probability, exactly. Okay, so what are we going to look at? We're going to look at a convex relaxation, essentially, of this non-convex problem. And there's another reason for why we study these kind of max margin classifiers, which is implicit bias. This is going to be in the next slide. And what we'll look at is how are the rates for this classifier, both for the noiseless and the noisy case. Okay, this is here the two questions that we're going to answer. Okay, so again, why do we care about this max LP margin classifiers with p between 1 and 2? So first, they're natural estimators to look at because this is what you get if you run steepest descent on the logistic loss with this particular norm here instead of. So the typical steepest descent would be p equal to 2, but you could choose any p from 1 to 2. And they're essentially the results here. Tagorsky proved it for p equal to 1, and these people proved it for arbitrary norms. That you'll get the max norm. Whenever norm you have here, you get the max this norm margin, so which is equal to the minimum of that norm subject to these constraints. Okay, this is just, So the margin is 1 over this. That's why it's called max margin. And here you have the minimizer, just in case you're confused. Okay, this is why we are interested in these classifiers, the natural objects to occur. Generally, these max norm or min norm solutions here are of interest because a lot of literature has been about implicit bias of first order methods converging to min norm solutions, and that's literally our motivation to study this particular convex relaxation. Okay, so this is again, you can view this as a convex relaxation of this. It's one of the possible ones. Okay, so let's go to the questions. The first one is for the noisy case. The noisy case, this is related to double descent, and that's why I do this first. The focus in previous works was for p equal to 2. And there, the typical kind of intuition is that you need spike covariances, meaning essentially a lot of mass on certain subspace of your d-dimensional space and very little probability to sample from the other directions. You still need them. In that case, you can actually get a classifier that is consistent in the sense that if n and d go to infinity, you'll get an error that goes to 0. However, we're focusing on the isotropic case. I actually did not I did not say this or emphasize this enough in the setting. So we assume that x are actually Gaussian normals with isotropic covariance. In that case, right, if you have literally only this min L2 norm, inductive bias, you don't really know where to search. Even if you're sparse, you really don't know where to go to. And hence, you're not going to have consistency unless you kind of have a spike covariance which is already aligned with the direction of your ground truth. Okay. So for isotropic Gaussians, we have a high error. And the reason is because we don't really know where to search. We have the statistical bias problem. Okay, so p equal to 2 was the focus. And we were essentially trying to populate this axis towards p equal to 1 and also in between 1 and 2 to see what happens, right? Because for linear regression, it seemed like we have the intuition p equal to 1, inducing sparsity is helpful. Is this true for classification as well? And also, is this true when we are interpolating noisy data? So basically, if you are familiar with our line of regression work, this is quite a similar story. But if you're not familiar, that's why I'm going to mention it briefly. P equal to 1 is consistent for the isotropic Gaussian case, but still slow. And so before our work, there were, so first of all, for the regression case, we did see consistency already. But then there were works on classification that had O of 1 upper bounds. And the question was, okay, can we also achieve consistency? And we proved, yes, we can achieve consistency for the classification case as well. And it's also of the order 1 over square root log n, essentially. And so if you plug in d is of the order n to the beta, and beta is larger than 1, and then you have a rate of 1 over square root log n. That's the way you should think about it. I think I have it here. Right, so if beta is bigger than 1, you're in the over-parameterized case. And then you can interpolate. And then you get this rate 1 over square log n. Yep.
The specification case is the min-max rate, no?
Yes, this is actually what I was trying to say here. There is this work from Jacques et al. That have this.
Min-max. Okay.
Yeah, but okay. So this is for the noiseless case.
Yeah.
For the noisy case, actually, sorry, it's a good question. This is the best known. I don't know if the proof is actually. I'm not sure if there's actually a minimax rate for the noisy case. But this is the best known, and it's kind of like it's hard to beat intuitively, right? So 1 over square root n.
I think it's log of p over s, but that's a smaller thing. But I was wondering, that's for the solution of that problem.
Yes. It could be better. Yeah, it could be better.
That could be a better argument.
Yeah. So exactly. It could even be better, but what we're saying is we're even far from this case. So yeah. So it could even be better. Actually, sorry. Yes. So there is a work that is I actually didn't mention on the other case. There is a work that is a recent work actually that is showing a lower bound as 1 over square root n. Sorry. Yeah, so this is I forgot. This actually they have a lower bound there. Yeah, and it's achievable by this regularized, or not regularized, but sacrificing data fit kind of.
Excuse me.
Yeah.
What does a small lower bound mean? You're saying it achieves a lower bound which is small. What does that mean?
So the lower bound is
Small.
No, it's just it's faster than this upper bound that we get.
So is it an upper bound or a lower bound?
No, this is a lower bound.
Okay.
But it's also an upper bound. So my point is that
Is she doing something impossible?
it's achieved by this. Okay, it's achieved by this, and it's also optimal by this newer paper 2018. Okay, so this is achievable, and it's lower and upper bound essentially.
But it's not interpolating, or it is?
It's not interpolating, yeah.
Okay. You're. Sorry, I walked in late. I
Yeah, no worries.
You're interpolating?
Yes.
Okay.
So we have these interpolating in that sense.
Yeah.
Basically training error 0.
A quick question.
Yeah.
So your bound kind of diverges because it's log d over n when d gets close to n.
Yeah.
Now, you have
not
you have an equality.
Yeah, it's actually inequality. So it's upper and lower bound actually. So it's not like this is tight in the constant of this leading term. Yeah, sorry. Thanks for the questions. Okay. So the point here was literally that the max L1 margin classifier has a very slow rate. And it's much slower than what's possible, both in terms of theoretically lower bound, but also in terms of an upper bound achieved for a different estimator. Information theoretically, it's possible, and some estimator achieves it. That's not interpolating. Okay, that's for LP, p equal to 1. And what's the reason there? Why is it so slow? Why is it 1 over square log n? And so the intuition is that for p equal to 1, we have the opposite problem. So the bias is actually the good one, right? So we're trying to search for sparse solutions, and the ground truth is sparse, so this is the right inductive bias in that sense, but the variance is going to be large because we're going to, so this is an intuition that, right, so in that case, if you have to interpolate, and you have to interpolate noise, then if you shrink your flexibility of your function class, you have much less degrees of freedom to distribute your noise in different directions. So it's going to hurt your performance more in that sense, right? So this is purely due to the noise and purely due to the fact that you have to interpolate. So otherwise, if you can say, okay, I sacrifice some data fit, then I don't have to make sure to distribute the noise in the sparse directions. I can just ignore it, then it's fine. But if I have to do that, then essentially because my flexibility is smaller, the effect of the noise will be larger. That's some intuition you can think of. That's the one that I'm using, basically. Okay, so here we have the problem of high bias for p equal to 1. So then, if you look at it, you might wonder, okay, is there something in between that has a good rate that is optimally trading off bias and variance? And so I think I won't go into a lot of detail here, but basically the answer is yes, we can get polynomial rates, not just log rates, in between of order 1 over n to some power. And I think, I don't have that, the actual concrete plot here due to the interest of time, but basically we can get the rate of 1 over square root n for beta bigger than 2, and for some p in between 1 and 2. And it's very close to 1. So that's possible, but the concrete rates are very complicated and depend on p and beta in a complicated way. I don't have time to describe that. Another caveat is, so this is what I meant. We have some log factors, but essentially it's 1 over square root of n. And so another caveat is that we only have the analysis for p larger than 1 plus 1 over log d. That's due to some concentration that we're using there. But that's, at least we can find a p for beta bigger 2 such that we get 1 over square root n. And it's important that it's not close to 2, but close to 1. Yeah.
So just to understand, the higher level aesthetic principle of this work, an idea that comes to mind is use the minimax procedure, which is not trying to interpolate, and then find the interpolator that's closest in L2 or something like that. Does that make sense?
You mean the average margin one? It's like a two-step thing?
Definitely a two-step thing. I forget the name of the. I forget who it was the slide earlier matching the minimax rate. And then does it make sense to then just look for an interpolator that's closest to that in some norm? I think L2 would make sense here because we're dealing with MSE, right? Is that the error metric?
Yeah. I don't think that's going to give you a similar estimate. I mean, that's quite it's contrived to think about these whether two-stage and also you can think about elastic net, right? Is it similar to this P in between?
Yeah.
I think they're all quite different, and at least.
Well, I'm not to suggest that it looks like this. I wasn't trying to suggest that. I was just suggesting it as an interpolation scheme that might be easy to analyze.
Had quite a few, also for regression. Also, did you have for classification as well?
I just looked at it for regression, and it is contrived, so I didn't pursue it.
Yeah, exactly. So, but she has a case where you have the two-stage interpolator, and then it achieves a good rate.
I will point out that there's an interesting work, I think, by Rong Gay and a student, which has not been noticed by a lot of people, but they show that you can get this type of hybrid interpolation through some diagonal network, and just naturally.
Okay. Hybrid meaning, but
like
not
what
like.
I was mentioning, like
but not
kind of what Dan is saying, like this L1 plus L2.
Yeah. Okay, you mean there's a 2 stages
You
kind
can
of
get
a
it naturally through optimization.
Yeah, that's cool. Yeah, thanks.
Which I think is interesting.
Okay, so this is how much time do I have? 10.
20 minutes.
Huh?
20 minutes.
10? Okay.
Well, that.
Yeah, but
then
I won't take that long. Yeah. Okay. So this is essentially just a summary slide for what we now know about the max LP norm interpolators between P and 1, and what can we learn from that on a high level, right? Because it's a very particular classifier, and so what do we learn from this? On a high level, how I view this is, right, so the ground truth is sparse. So for p equal to 2, we have 0 inductive bias towards the ground truth, towards the structure of the ground truth. For p equal to 1, we have a very strong inductive bias towards the ground truth, sparsity. Right? And so in the case where we have to interpolate noise, or where we are interpolating noise, if you have a strong inductive bias, a too strong inductive bias, you have the problem of variance. So if you want, like if interpolator does well, it generalizes well, it needs to be somewhere in between, right? Not having too strong of inductive bias and not no inductive bias, because both extremes are bad. But this is perhaps a bit unintuitive in the beginning when you think about it. So what could be inductive biases in the real world, which are not just sparsity? I mean, you can think of, we actually did these experiments, I don't have them here, for neural nets, right? So what could be some structure that you know your data really satisfies? For example, if you think of remote sensing, when you have patches of land, agricultural and residential, and you want to classify between those, these should really be rotation invariant, right? So if you rotate the image, you should get the same label. This is also some sort of structure of the ground truth. It's invariant to these rotations. And this one you could, for example, try to enforce, right? So by data augmentation, for example, you can enforce this transformation invariance. You could also have a network that is invariant. And so what we're essentially saying is that if you have a lot of noise in your data, perhaps you shouldn't try to overly constrain that model to have this strong inductive bias. And so we did some experiments. I have them if someone's interested as backup slides later on, where we did this experiment with the remote sensing data, for example, and we saw some curves that look a bit like this. Okay.
Is it because the noise doesn't respect the symmetry, or can you explain more about why?
I mean, that's kind of the intuition I was trying to convey earlier. As if you're reducing, usually you think reducing flexibility is good, right? So, and if you can sacrifice data, so, and so you kind of enforce a 1 and you have some reasonably large lambda, and then it's good, right? But in the case where you cannot sacrifice, where you have to fit the noise, that it will just hurt you more in the smaller. Say you have only a few sparse directions. Say it's like L0, right? So it's only a few directions, D directions that you can actually fit. And you want a 1 sparse vector or something. Then the noise has to be fit on these very few directions. So in the directions of the ground truth, it's going to have a large effect, right? Whereas if you have a less inductive bias, you can just spread the noise everywhere and then have, in average, very little effect. So that's just the general kind of gist. Okay. So this is the high-level takeaway. We do have some experiments on neural networks that I don't have here. This is for the max LP margin classifier, or hard LP margin SVM. It's the same. This is a synthetic experiment where we actually did exactly this, the setting that I described before with Gaussians and linear ground truth. And then we ran logistic regression until, not logistic. We just did LP max margin. And you get, basically, if you add noise of different levels, you see different P's are optimal for different noise levels, right? So if you don't have noise, you want P equal to 1. if you add a bit more noise, you want this p to be moving towards 2. So that's what you can see in experiments. Even though our proofs are for the very high-dimensional setting, in experiments you can even see it for smaller, for this kind of simple d not too large. It's still large, but okay. And in the real-world experiment, and this is the leukemia data set we kind of really severely subsampled. There's also a very high-dimensional regime then. In that case, you can also see if you don't add additional noise. So we just, and this is a data set we assume to be not have a lot of noise, because our 0-1 error is also kind of small for the noiseless case. So we assume, okay, it's probably fine. And if you add more noise, you want to move towards less inductive bias towards sparsity. That's the same story. Yeah.
So if I caught what you said earlier, you were saying that the value of p you get from the theory is closer to 2.
Yeah, it's closer to 1. I mean, it's close to 1, but it's not equal to 1.
Yeah. Okay, so I misheard you.
It's just moving towards 2 as you increase noise. That's kind of what you can.
Yeah,
think.
and then I have another question, which is, so sometimes when you have lower bounds, it's like, it's just it's a particular distribution that has to be carefully crafted in order to achieve that lower bound, right?
Yeah.
Here you have a synthetic data where did you have to, so.
This is actually following exactly the distribution assumptions we need, which is Gaussians, and unfortunately very strict. But here, this is not a Gaussian, so that's what we found quite interesting, right? So here, we don't know the distribution of that data set, with the covariates. Yeah, but the proofs, both for regression and, actually for classification, they only work for Gaussian. For regression, we also have sub-Gaussians now, and for nonlinear. But this generally, this proof techniques that we used for classification is very particular for Gaussians, and that's one caveat of this whole line of work. Okay, so yeah, for the last 10 minutes, I did want to point out something I found curious for the noiseless case. The noisy case is essentially in the line of work of benign overfitting, double descent. But then we also thought about the noiseless case, which are these max L1 margin classifiers adaptive to sparsity in the same way as they are for regression? The basis pursued is adaptive to sparsity for regression. So here is the regression part. Right, so if you have sparsity of your ground truth, then you can do a convex relaxation of the non-convex problem and get a perfect recovery for n of the order, with high probability with n of the order S log d. The same as for the non-convex problem. And so both the convex relaxation is similar to the non-convex version that gives you the same rate, and we have adaptivity. Because if you don't have hard sparsity, then you don't get this rate, right? For classification, we can ask the same question. Right? So in the noiseless case, you can achieve this error with this BAIHT kind of algorithm. But what happens when you look at this convex relaxation? And so this is unknown, and this is basically if you just rewrite the max L1 margin classification, it's the same problem. And so it's unknown whether you also get the same rate here. Okay, so this is something we were just curious about, what happens in the noiseless case. And actually, what we could prove was very surprising to us, at least. First, there were some works before us that were saying there's an upper bound of order 1 over n to the 1/3 for any W star, you can get this rate. Right? You just plug in your W star, so if you have a small L1 norm, you have a smaller constant there. But it's of the order n to the 1/3. And they conjectured that a sparse W star should yield a faster rate. Right? So maybe like at least 1 over square root n or something like this, if not 1 over n. And so we proved that actually this is not true in the sense that even if you're sparse, like, if you're sparse in that sense, like S is much smaller than N, you will still get this 1 over N to the 1/3 rate with some polylogs, but you will not get a substantially faster rate than if you than for any W star. So even if you add this constraint, you'll have this slow rate. If you use this particular solution, right? So that's somewhat strange, right? If you now look at the summary slide back here, this is definitely not the same story, regression classification. Okay, so what's the intuition why this max L1 margin classifier doesn't work? I mean, that's only a very small kind of a high-level intuition. So for one, the max L1 margin classifier will have a margin that is larger than n to the minus 1/3. And the problem is that the ground truth does not have a large L1 margin. So if you look at the same value, plug in this value, plug in W star, you get something smaller than n to the minus 1/2. So this inductive bias is actually a very bad one, right? So usually you know that our inductive bias originally is if you want a small L1 norm, you know the ground truth has a small L1 norm, and it also y minus x W star of the ground truth is going to be small. So these are all like good things you throw in there. But then this component here, which is the actual margin, it has the actual margin is very small for the ground truth. So this is not perhaps a good cost function to have in your optimization problem. Okay, so primarily our result throws, for us, actually opens up more questions than it answers than we thought originally maybe we could actually get at least a square root 1 over square root n rate, but didn't manage. And actually it's much worse, right? So this is what we get. But then if you think about this regularized problem, or the average margin formulation, they get this 1 over square root n case, even in the noisy case, right? So that means that this convex problem will also get 1 over square root n in the noiseless case. So somehow there's a big gap between the margin formulation and the average, like the max margin, okay, so this margin, which is the minimum overall, right, versus the average overall. So that's why I say swap min margin with average margin. So one thing you could wonder is if you replaced this min by the average, can you prove this also that it is generally a better estimator for the noiseless case? But then the question is that a reasonable estimate to look at, in the sense that is this an implicit bias of some method, first order method, for example? Right? Because otherwise, I mean, there's many solutions we could study, but is this a reasonable solution that we would encounter in practice? Like Vidya said, maybe the two-stage one naturally occurs for certain networks. Like, is this also something reasonable to think about, or maybe some loss function that also yields this? Maybe, maybe also not just that, but also maybe this is a solution if you early stop when you run first-order methods on something. This could also be true, right? So because if you have any loss function that's reasonable, if you run long enough, you should not sacrifice data fit. So the question is there some sort of early stopped implicit bias of some method? Okay, third question perhaps. If you look at all the results we've seen in this talk, then you get this weird picture. So for p equal to 2, we have inconsistency, even in the noiseless case, because we don't know where to search. Then for p equal to 0, which is the non-convex case, we have this rate 1 over n, noiseless case, and minimax. Then we have for p equal to 1, this 1 over n to the 1/3 for this mixed margin classifier. And in between, somehow we get a rate for the noisy case of 1 over square root n, right? For this regime of d of the order n to the beta. And so what is this weird curve now? Like, so when I put everything together, I was really puzzled when I was looking at this, and I don't really understand. Why is there this bump, essentially? And yeah, why is there the bump? And why does p in between 0 and 1 do better in this case? Or does that, and then the next question, does this correspond to some implicit bias of some network? It's always the question behind. And so for the bump here, because I really didn't believe this. I was like, is this real? So I just asked my student to run a couple of experiments for just synthetic experiments. Is this only something theoretical, high dimensional, or some artifact of the proof or something? But actually, you can see this if you just run experiments in the very high dimensional setting. Here, these 5k and n is small, and I really see this bump here. That for p in between, in the noiseless case, you get a better MSE. But then the effect goes down if you get more and more samples. So there seems to be something real about this bump between 1 and 2. And yeah, this is also something quite weird that one could study. And we don't understand as of now. I don't think the community understands. Okay, so I guess I'm also done with the talk now. Let everybody go to lunch. So this is just a few papers. The 2 papers I mentioned today, one is on the noisy interpolation case, one is on the noiseless case. And yeah, if you're interested in neural network experiments that kind of test whether the hypothesis with this inductive bias can translate, you can also have a look at that paper. Thanks.